So how do we represent our real numbers? As I mentioned yesterday, all the real numbers can be placed on the number line, sometimes known as the real number line. So we could represent them geometrically. So that's physically using the number line. There's the picture, and we put a dot at the point we're talking about, something like that. We can represent them algebraically via a solution to an inequation or an equation. There's another notation which you may or may not be familiar with called interval notation, and we often use that when we talk about the domain and range of functions. Then there's set notation, yet another way of describing all the possible real numbers that we're talking about. It's a much more formal way. Types of intervals. You can have what's called a bounded interval. So it has endpoints. You could have an unbounded interval. So that's something that only has one endpoint. And then you could have a closed, and that's when the endpoints are actually included. So it's like a less than or equal to. And then finally you could have an open one, and that's where the endpoint is not included. Degenerates, great name, isn't it? It's just simply a single point. So it's not really an interval, we're just talking about a single point. It's degenerate. Well, let's have a look at all that. So here's an example. If I was talking about the interval x is greater than 5, well, on the number line it would look something like that. Now, I'm not sure how you draw your ones. I always like to put the line above the number line itself so it doesn't get lost. Sometimes if you draw it on the number line, you lose it with the number line itself. So that way it's very clear. That is open, unbounded interval. Right? It's open because the point 5 there, the boundary is not included, but it's also unbounded because on the right hand side it's going off to infinity. It doesn't stop. So that would be an open, unbounded interval. Interval notation, it would look like that. Open parentheses and closed parentheses we use when the endpoints are not included. So if we're going off to infinity, well then we say, well, that endpoint's not included because of course you can't really get to infinity. So that's why we've got a closed parentheses on that one. Set notation, so I put it in braces, and so we've got x. The colon means such that. So all the x's such that x is greater than 5. So that would be a more formal way of writing the interval there. Okay, x is less than or equal to 6. The difference here is we colour in the dot to indicate, hey, the endpoint is included. So that one's a closed, unbounded interval. And now we use a square bracket. The square bracket indicates that the boundary point is included. So one that goes in between 4 and 6. So there it is on my diagram. That is open. Again, they're not included, but it is bounded. So 4 and 6 are the boundaries. We're just not including the boundaries. And so we'd have open parentheses on both of those. -2 less than or equal to x less than or equal to 1. Now we colour in the boundaries. So that's a closed bounded interval. And we have square brackets on both of those. Here's one where one boundary is included and one's not. So we have an open circle on the 2 and a closed circle on the 4. We just call that a bounded interval. Is it open? Is it closed? Well, one end's closed, one end's open. So we say it's bounded. The rational numbers. We talked a little bit about that yesterday. Rational numbers, of course, are any number that can be written as a fraction, but of course we must have integers on top and bottom of the fraction. I mean, something like the square root of 2 on 3 is still a fraction, of course, but it's not rational because square root of 2 is not an integer. Irrational numbers is the complement of rational numbers. If it's not rational, it's irrational. And that's all the prefix IR really means, is not. So any other number is irrational, but all irrational numbers can be written as a unique infinite decimal. And so it goes on forever, but never repeats, and it'll be unique. Each irrational number has its own particular sequence. We're going to prove that the square root of 2 is irrational. So how do we prove it? And the method I'm going to use here is proof by contradiction. So the idea with proof by contradiction is actually we will assume the opposite. So I'm going to assume actually that the square root of 2 is rational. Well, if it is rational, then I know I can write it as a fraction where a and b are integers, and have no common factors. So let's assume we've simplified it down as far as it can go. So there's no common factors there. If I rearrange that, I get b root 2 is equal to a. Square both sides. 2b squared is a squared. So therefore, 2 is a factor of a squared. So a squared is divisible by 2. But hang on, if a square is divisible by 2, it must be divisible by 4. Because in squares, all factors are doubled, if you like. Because you've got a times a, b times b. So if 2 is a factor, there must be another 2 in there as a factor. So you've got 2 times 2. Okay, so we know it's divisible by 4. So I could rewrite 2b squared as 4k, where k is some integer. Well, that means b squared is equal to 2 times k. Hang on, that's telling me that a squared and b squared are both divisible by 2. Well, if they're both divisible by 2, they have a common factor. But we said right at the start, a and b are integers with no common factor. So I've just contradicted myself. I started off by saying they have no common factors and end up proving that they do have common factors. So therefore, my original assumption must be false. So square root of 2 is not rational. In other words, it is irrational. Just a little bit about significant figures. Irrational numbers, let's say you can't work them out exactly. That decimal just keeps going on and on and on and never stops. So yes, sometimes we have to accept an approximation, depending on what we're doing. So when we do approximate, we're either going to say, oh, round it off to so many decimal places. Sometimes there's that. But the other way we could do it is to so many significant figures. Rounding off to so many decimal places, hopefully we've got under control. Let's more talk about significant figures. And that's pretty much it. Just start at the first non-zero digit and just count the required number. So, 0.050703 to 2 significant figures. Well, the first number there that's not 0 is the 5. So I'll start counting. 50, round off, there is 0.051 to 3 significant figures. 507, round off, 507. 4 significant figures, it becomes 05070. That 0 is very important when we're talking about significant figures. Now, whole numbers can get confusing. I'm going to round this off to 2 significant figures. First number that's not a 0 is 3. So I'll start at the 3, I'll count to the next one, 0, round off. Oh, okay, so it's 3,000. 3 significant figures. I'll start at the 3 and I'll count, 1, 2, 3, round off. It's 3,000. All right, let's do it to 4 significant figures. I'll start at 3 and keep counting. It's 3,000. They're all the same. Because the point is, those zeros there have other meaning, and they're holding place value. And if we were to get rid of them, we'd change the number. So they have another role. If the answer is ambiguous, scientific notation should be used. When we've got 3,000, 3,000, and 3,000, that's telling me nothing about how many significant figures there are. And so what that's saying is that's when scientific notation would be appropriate, because then I could write the first one as 3.0 times 10 to the 3. The next one I could write as 3.00, and the last one 3.000. Because those zeros are now behind the decimal points, I know they're significant. So how do we find how many significant figures a particular number has? Same idea. Start at the first non-zero digit and count until the end of the number. So there's how I'll point 0.05. So how many? I'll start at the 5. 1, 2, 3, 4, 5. 5 significant figures. And look, those zeros in between the 1 and 3, because when is the 0 significant? When is it not? Don't worry about it. Just start at the first number and count to the end. So we've got 1, 2, 3, 4. That also has 5 significant figures. Oh boy, look at all those zeros. Same rule. Start at the first one. 1, 2, 3, 4, 5. 6 significant figures. Yes, if I got rid of that 0, the number wouldn't change. And that's why it's significant. It must be there for a reason. Perhaps it had something to do with the measuring instrument that I was using, and it just happened to land right on the division. And so I had to write 0 down. Oh, but what about these whole numbers? We just saw, is it 2, is it 3, is it 4? So this one here, my answer is, well, there's 2, 3, or 4. That's usually unsatisfactory because they like a definite answer. So if I had to write an answer for that, I would say 4 significant figures. I might not be right, but I can't be wrong with the information they've given me. So if it is, again, ambiguous, I'm going to give the largest one. I'm going to give the largest possible answer. So that's the first bit for today.